morning, students. I'm Chaitanya, Assistant Professor in Mathematics, working in Institute of Aeronautical Engineering, located at Dundigal, Hyderabad. A very warm welcome to you. Today, I'm going to discuss on moments, skewness, and kurtosis of a continuous random variable. Okay, and Gaussian approach of dimensionality reduction, especially in machine learning. Okay, so as a part of our course curriculum, probabilistic and modeling and reasoning, we are in second module, that is the continuous distributions and Gaussian approach, in which now we are going to discuss the moments, skewness, and kurtosis of a probability continuous distribution. So before going to the concept of moments, skewness, and kurtosis, I'd like to discuss the importance of Gaussian approach or the Gaussian distribution in machine learning, especially dimensionality reduction. Generally, a sample of data will form a distribution. If you see the distribution of sample data over a two-dimensional plane, generally it will be in the form of a normal distribution. The data will be most probably in the form of a normal distribution, which you come across in your course probability and statistics in your second semester. So that is why Gaussian distribution plays very important in analyzing the data sets. Okay, and helps in reducing the dimensionality of a data set. Okay, right. Now, see, a Gaussian process is any process in time or space. First, what is a Gaussian process? It's nothing but a continuous distribution, continuous moment. Generally, we have two physical variables, namely time and space, which are continuous every moment. The time is a continuous and the space is also continuous in our universe. So generally, to analyze the time and space, we use Gaussian process. And the other side of the coin, Gaussian approach or the Gaussian distribution plays a vital role in machine learning, especially in solving the problems like non-linear regressions and dimensionality reduction of a data set. So our course of interest is the dimensionality reduction, and in the dimensionality reduction, the Gaussian approach has a very vital, important role because we'll use to calculate the variance of the data set, and we'll try to find among those data sets which is having the largest variance, and basing on this largest variance, we'll try to reduce the dimensions, and that is why this Gaussian distribution plays a very important role in the reduction of data sets, and it has very wide applications in deep learning as well as the machine learning. Okay, it's just a brief introduction. We'll see more detail in the next coming lectures. Now let us focus on the theme of this lecture, that is the moments, the moment generating function, and the skewness, kurtosis of a probability distribution. Okay. So first let us define what is a moment generating function of a random variable. See, the moment generating function of a random variable X is defined as expectation of e power t cap x. Let us recap what is expectation of a random variable. The expectation of a random variable is defined as summation x into p of x, where x is equals to 0 to infinity for a discrete random variable, and integral minus infinity x into f of x dx in case of continuous random. So with the motivation of expectation of a random variable, we can also define this as summation e power tx p of x in case of discrete random variable, integral minus infinity to infinity e power tx f of x dx in case of continuous random variable. So when we calculate this expectation, it leads to a function of t which is denoted by m of t, which is called the moment generating function of the random variable X. So the moment generating function, which is denoted by m of t, is nothing but expectation of e power tx, which is given with the help of these two things in the case of discrete as well as continuous. Let us try to understand it more implicitly. Yes. Uh, Let us try to understand what are moments. Now we have understood what is moment generating function. Now we are going to understand what are moments. Okay. So let us take the definition of moment generating function e power expectation of e power tx. So we know the exponential function, that is e power z 1 plus z by 1 factorial plus z square by 2 factorial plus z cube by 3 factorial and so on. So with the help of this, we can write e power tx as 1 plus tx by 1 factorial plus t square x square by 2 factorial plus t cube x cube by 3 factorial and so on. Okay, and now let us apply expectation on both sides, because we have to calculate the moment generating function. We need to apply expectation on both sides. That is applying expectation on both sides. Here t is treated as constant and it can be written as outside. That is why we get expectation of 1 as 1 plus t comes outside, expectation of x by 1 factorial, t square comes outside, t square into expectation of x square by 2 factorial, t cube into expectation of x cube by 3 factorial, so on, t power k into expectation of x power k by k factorial and extended. So this is a kind of expansion of e of e power tx. Now here we are having the quotient of t as e power x, e of x, and e of x square the quotient of t square, e of x cube the quotient of t cube, and e of x power k the quotient of t power k. Now these quotients e of x square, e of x cube, and so on, e of x power k are denoted by mu1, mu2, so on, mu k, which are called the moments of the probability distribution represented by the random variable K+. So e of x square, e of x cube, which are shortly called as mu1, mu2, mu3, so on, mu k, are known as the moments, and this function, this expansion is known as moment generating function of the random variable K+. Okay, so here now we are going to find the moment generating function. Okay, let us look into the expansion of e power tx, which I have explained just now. The exponential form, that is 1 plus tx whole square, tx whole cube, so on, tx whole power k. The denominator is 1 factorial, 2 factorial, so on, k factorial, and expectation e of 1 is 1, e of x square, so on, e of x power k. Now let us rename e of x as mu1, e of x square as mu2, so on, e of x power k as mu k. So we get this expansion, and this mu1, mu2, so on, mu k are called moments. Okay, moments. Now we can understand these moments. Let us suppose this answer is m of t. For the time's sake, if we apply some mathematics, we can compactify the expansion and we can obtain a function in terms of t, which is nothing but m of t, the moment generating function. Now we can also understand these moments in terms of derivatives. Let us look into that aspect. Here, if we derivate this m of t with respect to t, and if you substitute t is equal to 0, you will get mu, the first moment. If you derivate the m of t 2 times with respect to t, and if you substitute t is equal to 0, you will get the second moment. So in general, if you differentiate it for k times with respect to t, okay, the m of t, and if you substitute t is equal to 0, you will get the kth moment, that is mu. So every moment is nothing but the derivative. Suppose second moment is second derivative of m of t, third moment mu3 is third derivative of m of t, kth moment is nothing but kth derivative of m of t with the substitution t is equal to 0. So moments are nothing but the derivatives, the rate of changes in the moment generating function at origin, that is t is equal to 0. That we can understand, that is time 0. Okay. So this is two kinds of perspectives over moments. Okay, right. Now, so let us understand it more vibrant way with the help of calculating moment generating functions for some very important discrete random variable distributions, that is binomial, Poisson, and also we look into the moment generating function of the famous normal distribution. Then we'll go to the concept of skewness, and which is followed by the concept of KURTOSIS. Okay, so first let us try to calculate the moment generating function of binomial distribution. So let us start with the definition of MGF, that is e power expectation of e power t cap x. Let us recap what is the probability function of a binomial random variable NCX p power x q power n minus, which is very well known to you in your probability and statistics course curriculum. P of x is NCX small p power x q power n minus x. Okay. Now, where x is equal to 0, 1, 2, so on, which is nothing but probability of winning x times out of n trials. Probability of winning x times out of n trials. Okay, where p represents your success rate and q represents your failure rate basing on your previous performances. So the probability of winning x times over n trials is nothing but NCX p power x q power n minus x. Suppose you are playing a bowling game. You have a record of 75. That means whenever you make 4 trials, you used to succeed 3 times in hitting the stump with your ball, and your failure rate is 0.25. Now you are given 6 chances. You have to hit, in order to qualify to the next round, you have to hit the stumps for at least 4 times. Then your probability of hitting at least 4 times the stumps, that is 6C4, 0.75 whole to the power 4, 0.25 whole to the power 6 minus 4. That is. By calculating this, you can assess your chances of winning and to qualify to the further round. That is the advantage of binomial distribution. Now we are going to calculate the moment generating function of a binomial distribution. See, the binomial distribution, the moment generating function, let us start with the definition e power t cap x, which is nothing but summation e power t x p of x, where x is equal to 0 to n. Here limited number of trials, and that is why we are writing x is equal to 0 to n. Now let us substitute summation x is equal to 0 to n e power tx. What is p of x? The binomial function, that is ncx small p power x small q power n minus x. Okay, that means we have substituted the binomial function formula, that is ncx small p power x q power n minus x. Now, if you keenly look at this, the power x and the power x, we can club them. That is, we can rewrite it as x is equal to 0 to n ncx e power t into p whole power x q power n minus x. That means we have clubbed the powers x, x. That means we can club the powers, as powers are x, we can club the base, that is e power t into p whole power x. Okay. Now, let us retrospect into binomial expansion, which we have studied in our 10th class. That is a plus b whole power n nc0 a power n b power 0 plus nc1 a power n minus 1 b power 1, nc2 is a power n minus 2 b square, so on, ncn a power 0 b power n. So this is binomial theorem we come across in our 10th class, which can be compactified as a plus b whole power. Now this can also be written as in the form of summation ncx a power x b power n minus x is equal to 0 to n. Isn't it? So right side can be written as summation x is equal to 0 to n 6 a power x b power. Now if you see, in the place of a we are observing e power t into p, and in the place of b we are observing q. That is why we can write it as summation e power t into p plus q whole power n by using this formula a plus b whole power n. We can write it as e power t into p plus q whole power n. So we have obtained the moment generating function of the binomial distribution, which is m of t is equal to q plus p into e power t whole power n. And by differentiating it with respect to t for one time and substituting t is equal to 0, we'll observe that mu1 is np, which is nothing but the mean of binomial distribution. Okay, and by differentiating it for two times, that is, this is the binomial distribution, the moment generating function q plus p into e power t whole power n. Okay, it is derivative for with respect to t, that is d by dt of m of t, which is nothing but by chain rule we can write it as n into q plus p e power t whole power n minus 1 inside derivative p into e power t. Now if you substitute t is equal to 0, you will get n into q plus p whole power n minus 1 into p. But in binomial distribution, p plus q is equal to 1. So this is nothing but n into 1 power n minus 1 into p, that is equal to np. Surprisingly, the mu1, that is the first moment, is equal to np, which gives us the mean of binomial distribution, which is np. In the same way, you can observe that mu2 is n square, of course mu2 as np. That means if you differentiate it for two times and if you substitute t is equal to 0, you will get again mu2 as np, and we can calculate the variance as mu2 minus mu1 square, that is np minus np whole square, that is npq. So with the help of moments also we can find the mean and variance. Okay, so that we have seen now. So mean of binomial distribution is np and the variance is npq. Okay, now let us go to the Poisson distribution. Let us try to find the MGF of Poisson distribution, and let us look into the mean and variance. Okay, so for that, let us go to the next slide. Here we are going to derive the moment generating function of the famous Poisson distribution. Let us recap the probability function of a Poisson distribution, that is e power minus lambda power x by x factorial, where x runs from 0, 1, 2, so on, infinity. So out of indefinite trials, what is the probability of winning x times? That is given by the Poisson distribution. Okay, now let us try to calculate the moment generating function of Poisson distribution. According to the definition, summation e power tx p of x is equal to 0 to infinity. Okay, so expectation of e power t capital X, where x is Poisson variable, is summation x is equal to 0 to infinity e power tx p of x. Now e power tx, what is p of x? Poisson distribution, that is e power minus lambda, lambda power x by x factorial, isn't it? Now, what is the variable here? Variable is x. So, this contains x, this contains x, this contains x, but this term does not contain x. So, that is a constant. It can be written outside. So, e power minus lambda comes out, and within the brackets, x is equal to 0 to infinity, the summation e power tx lambda power x by x factorial. Okay. Now, e power minus lambda, it can be written as summation x is equal to 0 to infinity lambda e power t whole power x by x factorial. If you expand this, this will be like the exponential form, that is 1 plus lambda e power t plus lambda e power t whole square by 2 factorial, so on. That is why we get e power minus lambda into e power lambda e power t, because it is like exponential form. We can compactify it as e power lambda. As bases are equal, this is the moment generating function. Bases are equal, powers can be added, e power lambda e power t minus lambda. Now, to calculate mean, let us differentiate it with respect to t on both sides, that is d by dt. D by dt means it is nothing but, okay, lambda into or e power minus lambda into e power lambda e power t. Okay, this is what. Okay, now let us substitute t is equal to 0. We'll get e power minus lambda into lambda e power plus lambda, that is by lambda. So mu1 is lambda. The similar way, by differentiating it for 2 times and substituting t is equal to 0, we'll get mu2 is equal to lambda square plus lambda. And variance will be given by mu2 minus mu1 square, that is lambda square plus lambda minus lambda square, which is equal to lambda. So we have seen that the mean and variance both will coincide in case of Poisson distribution, nothing but lambda, okay, with the help of moments and moment generating function. So this is the derivation that just now I have explained, okay, the moment generating function of Poisson distribution. And this tells us that if you take a random variable, we have a sequence of random variables x1, x2, so on, xn, which are independent, then we can construct another sequence of random variables as their sums. S1 is x1, s2 is x1 plus x2, s3 is x1 plus x2 plus x3, so on. Then for this new set of random variables, we can calculate the moment generating function, that is pi s1 as pi x1 and pi s2 as pi x1 into pi x2, pi s3 as pi x1 into pi x2 into pi x3. That is, if the random variables are independent, the moment generating function of their sums are nothing but the product of the individual MGFs. That means pi Sn is nothing but the product of the moment generating functions of the n random variables. Okay, and if these coincide, we'll get this equation. Okay, here we are having some problems which will be discussed in the next video. Okay, so now I'm not touching the problematic part in this video. We are moving to the concept of skewness and kurtosis of a continuous random. Before that, let us have a look into the moment generating function of a normal distribution. You know, normal distribution, the PDF is given by 1 by sigma root 2 pi e power minus x minus mu by sigma whole square into 1 by 2. You know this, where mu is mean and sigma is the standard deviation of the normal distribution. So we can understand, if the standard normal distribution 0 1, the moment generating function will be e power t square by 2. With the help of this definition, e power tx f of x dx or f of z dz minus infinity. You can integrate and you can calculate. I'm not going into that detail. And also we can see that the moment generating function of normal distribution is given by, where x follows normal distribution, nu comma sigma is given by e power mu t plus sigma square t square by 2. Okay, so the moment generating function of a standard normal variate is e power t square by 2, and general normal variate is given by e power mu t plus sigma square t square by 2. Standard means mean is 0, variance is 1. Not general means mean is mu, variance is sigma square. Okay, so this is the way we could see the moment generating functions of binomial, Poisson and normal. Okay, now we are entering the important aspect of continuous random variate, especially the Gaussian distribution, that is the measure of symmetry, that is skewness. Generally, when we plot the data on an xy plane, okay, suppose this is the mean of that distribution. Okay, suppose this is the mean of the distribution. Generally, the data may be stretching equally on both sides, or the data may stretch more towards the right side of the mean, or the data may stretch more towards the left side of the mean. So these are the three cases generally happens when we plot the data on an xy plane. The data may equal stretch on either side of the mean, or the data may stretch more towards the right direction of the line mean, and the data may stretch more towards the left direction. So in this case, the data is called perfectly symmetric distribution. That means it is equally stretched on both sides. In this case, the data is called positively skewed, and in this case the data is called negatively skewed. So there are three kinds of stretching of data about its mean, that is equal distribution, more towards right, or more stretching towards left. Equal, more stretching towards right, more stretching towards left. If it is equal, it is called perfectly symmetric. If it is stretching more towards right, it is called positively skewed. If it is stretching more towards right, it is called negatively symmetric. Let us look into the graphs. This is the Karl Pearson's measure of symmetry, that is the skewness. Skewness is the measure of symmetry of a probability distribution, and Karl Pearson has given a formula to measure the skewness, that is denoted by beta 1. This is given by the ratio of mu3 square by mu2 cube. You know, we can calculate the moment generating function, and hence we can calculate the moments mu1, mu2, mu3, so on. Now we are calculating beta 1 with the help of moments mu3 square by mu2 cube. And basing on the value of beta 1, we'll decide whether it is perfectly symmetric, or positively skewed, or negatively skewed. Okay, if beta 1 is equal to 0, then we call the distribution is perfectly symmetric. If beta 1 is greater than 0, we call it as positively skewed. If beta 1 is less than 0, we call this distribution as negatively skewed. Okay, so depending upon the sign, if beta 1 is neutral, then it is perfectly symmetric, equally stretched. If beta 1 is positive, then it will be positively skewed. If beta 1 is negative, then the distribution will be negatively skewed. Okay. Here you can see what happens in the three different cases, that is symmetric, positively skewed and negatively skewed. When the distribution is positively skewed, if you take the line x bar, the mean, that is if the distribution mean is x bar, and if you draw a line through x bar, then in symmetric distribution the data will be equally spread on both sides. That is, if it occupies 50 acres on the left side, then it will be the same, that is 50 acres towards the right side. It will be equally stretched, 50 acres, or 50 cents, 50 cents. So that is called symmetric, perfectly symmetric, that is perfectly stretched on both sides of the mean. The data is stretching equally on either side of the mean, that is called symmetrical distribution. In this case, surprisingly, the mean, median and mode, all the three things of the distribution will be coinciding. That is, mean will be equal to median, which is equals to the mode. So all mean, median, mode will be equal in the case of symmetrical distribution. Positively skewed distribution. Positively skewed distribution means the data will be more spread towards the left and will be less towards the right of the mean. Okay, and hence you can observe that mode will be greater than median, which is greater than x bar from the view of origin. Okay, so first you will see the mode, then median, then mean, and you will see that the right side of mean will have very less data occupied, and towards the left side you will see more data will be occupied. That is called positively skewed distribution. And in negatively skewed distribution, if you see, first you will see mean from the origin, you will first come across mean, then median, then mode. That is mean less than median less than mode, and towards the right of mean more data will be distributed, towards the left side of the mean less data will be distributed. That is negatively skewed distribution. So symmetric distribution, all the three will coincide, and positively skewed distribution, the mode will be greater than the median, which is greater than the mean, and negatively skewed distribution, mean will be less than median, will be less than mode. So this is about the skewness, and the measure of skewness is given by the Karl Pearson, that is beta 1. Okay, if beta 1 is equal to 0, perfectly symmetric, beta 1 greater than 0, positively skewed, beta 1 less than 0, negatively skewed. Okay. Now let us discuss the last concept, that is kurtosis. Kurtosis of a continuous random variate. Suppose the data is continuous, and if you have plotted the data towards the mean or xy axis, sometimes the data may be highly peaked, sometimes the data may be very highly expanded, sometimes the data may be balanced. That means it may be high altitude or very low altitude or balancedly altitude. That is called bulginess. Bulginess means narrow or very bulgy or balanced. Narrow, very extended or balanced. If it is very narrow, that means the height will be very high. The height will be very peak. That is called mesokurtic. That is called leptokurtic. If it is very balanced in height, it is called mesokurtic. If it is very, very less in height and very bulgy, that is called platykurtic. Okay, so depending on the bulginess of data, that means if the data is very bulgy and very low in height, that is called platykurtic. If the data is in the correct height and correct extension, then it is called mesokurtic. If the data is more high and very narrow at the ends, that is called leptokurtic. So leptokurtic, mesokurtic, platykurtic. Leptokurtic, mesokurtic, platykurtic. These kinds of variations we'll see when we plot the data on x4 plane. And there is a measure to calculate the bulkiness of the data, which is called kurtosis. So kurtosis is a measure of the bulkiness, that is whether the data is heavy tailed or light tailed or relatively normal, okay, which is called the kurtosis. Low kurtosis and high kurtosis and balanced kurtosis. Generally we see these three cases. Okay. Now Carl Pearson also given a measure for kurtosis, which is denoted by mu2, which is nothing but the ratio of the fourth moment with respect to the square of second moment, mu4 by mu2 square, and basing on the result of beta 2, we'll decide whether it is mesokurtic or leptokurtic or platykurtic. Suppose if beta 2 is equal to 3, then we call it as mesokurtic. If beta 2 is greater than 3, we call it as leptokurtic. If beta 2 is less than 3, we call it as platykurtic. Okay, that means in the mesokurtic, the distribution graph will be like this. In mesokurtic, the distribution graph will be like this. In platykurtic, the distribution graph will be like this. So meso is more height. Lepto means more height. Meso means balanced height, and platy means more flat, very less height and more bulky. Okay, this is called kurtosis. So you can understand all the three things in a single diagram: leptokurtic, mesokurtic, and platykurtic. Okay, leptokurtic means more height, less occupancy. Mesokurtic means balanced height, balanced occupancy. Platykurtic means more occupancy, less height. Okay, in this way you can understand. And this is called cumulative generating function. Suppose we have calculated the moment generating function for a random variable X, which is denoted by mxt, and if we apply logarithm, that is log of mxt, we'll get another function which is called the cumulant generating function. So moment generating function is denoted by mx of t, whereas the cumulant generating function is denoted by kx of t. And the relationship between the cumulant generating function and the moment generating function is nothing but log mxt is kxt. Okay, so the quotients of powers of t in moment generating function are called moments, which are denoted by mu1, mu2, so on, mu3. And the quotient of powers of t, that is t, t square, qq in cumulant generating function are denoted by cumulants k1, k2, k3, so on. So here also we t, t square, t cube will have some quotient which are called cumulants. Here also t, t square, t cube will have some quotients which are called moments. Okay, so that is the relationship between a cumulant generating function and a moment generating function. Okay, with this, I'd like to conclude the lecture, that is moments, skewness, kurtosis, moment generating function and cumulant generating function of a continuous random variable. So in today's lecture, we have discussed what is a moment generating function of a continuous random variable, how moments can be generated with the help of MGF, and also we have seen the MGF of famous distributions: binomial, Poisson, and normal. And we discussed the skewness, the three types of skewness, that is symmetric, positively skewed, and negatively skewed distributions, and kurtosis, the measure of bulkiness of the distribution, and three types of kurtosis, that is mesokurtic, leptokurtic, and platykurtic. And finally, we have seen the cumulant generating function and the relationship between the cumulant generation function and the moment generating function. With the help of this, I'd like to conclude today's lecture. In the next class, we'll meet with the Gaussian distribution properties and its emphasis in machine learning. Okay, and thanks for your patience listening. Thank you all.
Like, share, and subscribe. Hit the bell icon for more updates.